Okay, hello. So our project is super resolution using pixel subsampling. It is by me, Shyandeep Das, and Arunachalam. So in this project, our overall goal is to reconstruct and increase the resolution of an image that is taken by a very cost-effective camera, and and the camera has really bad bandwidth and hardware constraints on site. So we also need the sensor has like minimal computational functionalities. So we need absolutely least amount of computation on site, and the image quality itself is really poor. So we should have a way to increase the resolution at the final output, and we also need to reduce the size of the image before we send it, because there's really bad bandwidth constraints in the network as well. So we use two approaches to solve our problem. In approach A, we use L1 norm-based minimization compressive sensing to reconstruct the image and then convert it to a higher resolution output. And in approach B, we trained our own a neural network called and named it CS, which also does the reconstruction, and then we can use another neural network to give us the higher resolution output. So some related work, we are not the first ones to think of this. CSNet is a very popular, compressive sensing neural network that has been in the research world for a while now. The CSNet, how it works is essentially they have a network which calculates the sampling metrics for each of the images, and then send the sampling matrix for each of the different images to the receiver, and then the receiver has two different reconstruction networks to reconstruct the original image from these sampling matrices. However, there is a drawback to this approach. The site needs to run this neural network every time for each image and send that reconstruction matrix to the receiver in order for this to work. But in our problem statement, we have a really hardware constraint sensor on site, so that's not a possibility for us. And also there are other approaches using GANs. For instance, this paper from Ashish Bora, where they use a GAN network to estimate random vector in latent space, which is then used to reconstruct the original image. Then again, both of these approaches do require some amount of computation in hardware, which is not really a possibility in our scenario. So technical approach for for both of our approaches. So this is the main thing. How we actually achieve these like a really low amount of computation on site is by essentially using a completely randomized pixel selection of the input image. As you can see here, we have the original image. We, in this example, do a 25% random sampling of it using a mask, and we get this image, and then we send it to the receiver side, where we do compressive sensing to actually reconstruct the image, and a super resolution network which makes it the high resolution output.
So this is the first approach, that is compressive sensing using L1 norm minimization. So here we have the measurement matrix Y. This is the image which is there in the receiver side. A is the multiplication of the sampling matrix along with the Fourier basis, and we need to estimate H, which is the Fourier transform of the image. This is a underdetermined system of equations, and so we exploit the sparsity in H to find the vector elements. Once we find the vector elements of H, we use inverse Fourier transform to find the reconstructed image. The second approach is using our neural network called CONCS. We used 12,000 images from ImageNet to train the CONCS, and it was tested on 1,500 images. All the images were 64 cross 64, and the reconstructed images were of the same shape. We got good reconstruction with SSIM of more than 99%. We feed the output of the CONCS to the ESR GAN, which is a super resolution network to generate a 128 into 128 into 3 final output. So this is the architecture of the CONCS. Uh, the input basically consists of the sampled image, which is 25% of the pixels, uh, plus the mask, which is then sent to the convolution neural network. There are 4 con2D operations with the filter size of 3 cross 3. The activation is leaky ReLU here. As you can see, the input is has four channels, which is then after the first convolution, it is made into 8. From 8, it goes to we make it to 9 channels, and from 9 we made it all the way back to 3. And the final output is again moved from a 3 channel to another 3 channel, and we get the final output reconstructed image. So the ESR GAN is the Enhanced Super Resolution Generative Adversarial Network. This was a recent super resolution network from 2018. This was based on a well-known architecture, the SR GAN, and it improves on it by using a new layer called the residual and residual dense block. This super resolution network was trained on the Dev2K dataset, and this produces better looking super resolution images when compared to older existing methods such as SRCNN and SRGAN.
So talking about results and evaluation for both of these approaches now, we first let's analyze the approach of our our technical approach A. In the second image, as you can see, we have sent this we have had this original image, which is a 480 cross 480 image. We first downside it to 240 cross 240, and then we send only 25% of the image to the receiver, and then the receiver, using L1 norm minimization, reconstruct this image, which is again a 240 cross 240 image, and then we use the ESR GAN, as mentioned by Arunachalam, to reproduce our high resolution output. So we do this essentially to regain the 240 480 cross 480 output, and see the differences between the first input and the final outputs of the image. However, we do see some problems with this approach in technique A. The issue is when we try to do this with like really low resolution input. For instance, this input has a 64 cross 64 input, which was being reconstructed using L1 norm minimization. We find these artifacts in each of these inputs, and we have an SSIM value for this reconstruction was found to be 99.88%. However, in our second method that we used, we found much better results. So we used the same, we tried to reconstruct the same images again by sending this sampled image and the sampler mask in the input, and the reconstructed output was actually much better in this scenario. However, we do see a really stark color difference, especially in the third reconstruction.
So the CONCS was initially trained using the SSIM loss, which is structural similarity index measure. And while using that loss, the color shift was much higher. Now, using a combination of SSIM and mean square error, we have significantly reduced the color shift. And the color loss was measured on all the 3 channels, and it was found to be consistent. The output from CONCS was then sent to a super resolution GAN. The results you're seeing in this slide are from this ESR GAN. As you can see, from 64 cross 64, we've moved to 128 cross 128. And these are the 3 sample images. Now coming to the evaluation, the CONCS net was trained at 3 input image percentages, which is 25, 15, and 5. As you can see with the 3 different colors here. So the 25%, which is the blue line, and the orange is the 15 and the 5 is the green. At very low levels of image percentage, we see that the 5% outperforms the 25%. But at higher levels, the 25% beats out the one trained at 5%. We consistently see that 15% performs worse than when compared to 5%. And the con CS trained at 25% beats out the baseline. So now coming back to the baseline, we downsample the image to 25% and then upscale them. And then we compared the SSIM. So the SSIM for such images at 25% is 99.95, which is lower than the one which we achieved using con CS net 25. We also did the same for at 15 and 5. The SSIM of image from approach A was only 99.88, which was worse than simply downsampling and upscaling the.
Yeah, so as seen consistently throughout the results, our conf CS can indeed reconstruct an image with excellent structural similarity of more than 99%. And however, we do see some amount of color discrepancy and detail loss in the reconstructed image from our conf CS output. However, using a MSE and SSIM loss instead of using only SSIM loss did give us much better results in our reconstruction. So it might be worthwhile pursuing other losses such as PSNR and perceptual loss or MSSSIM, maybe to potentially get better results. And also, it would be a good upgrade to the network if the reconstruction was actually appended with the super resolution to do the reconstruction and super resolution in one go in one neural network. So that might be one future upgrade that this model can have. And also we can try to reconstruct and multiple images taken by multiple single pixel cameras using our conf-CS network. These are the references to some of the papers we read and learned a lot from while working on this project. And me and Arunachalam, we both would love to thank the professor for your guidance overall the span of the project, and your guidance really helped us in delivering a much better final result than we initially anticipated. Thank you.